This is Uberclamp, a reverse polarity protected, fast, self-resetting, current limited overvoltage protection circuit. It's designed to pass an input voltage through to the output through a low resistance path until the input voltage exceeds a certain voltage, in this case 6 volts. It then turns the output off and latches it off with a self-resetting cycle about every 2.5 seconds, so that if the input over voltage is removed, i.e. the input drops back down to the right sort of voltage, then it reconnects the input voltage to the load. During the turn-off, it delays turn-off by about 20 milliseconds, but it still doesn't allow the overvoltage to propagate through to the output, because it turns very briefly for those 20 milliseconds into a fast responding linear voltage regulator with a regulated output voltage equal to the trip voltage, in this case 6 volts. It turns off after about 20 milliseconds to avoid significant power dissipation in the output transistor here. At the moment we're connected to a 5 ohm load here, so it draws about an amp from the power supply. This 1k resistor here has got nothing to do with the operation of the circuit. It's just there so that when later on I remove this red wire from the terminal, you don't see lots of mains hum propagated through the scope, the pickup, from my fingers into the scope probe and causing a confusing trace. It's nothing to do with the circuit at all. At the moment everything's off. There's a green LED that says, yep, the output's okay. There's a red LED that says, no, we've either got an overvoltage or it's gone into current limit. And the current limit behaves the same way as the overvoltage protection, in that as long as the overcurrent on the output, which in this design is set to about 2.5 amps, persists, the red LED will stay on, but it will flicker because the circuit will retry about every 2.5 seconds to reconnect the input to the load. If it's in current limit, it stays in current limit. If the overcurrent is removed on the output, then at the end of the next 2.5 seconds retry cycle, it will reconnect the input to the load. Over to the scope. Yellow traces input voltage 2 volts per division. Magenta trace is the output voltage, 2 volts a division. They've both got a 6 volt offset, so this is ground. This, where there's a cursor as well, although you can't see it very clearly, is plus 6 volts. So up here is 10, 12. And this gives you a rough indication of the output voltage. I must point out that the metering in the power supply and here is not terribly accurate, so the voltages may not stack up exactly, and you don't see quite the output current that you might expect, but it's still sufficient to demonstrate the operation of Uberclamp. So let's turn it on with a 5 volt input, which is below the 6 volt over voltage protection, drawing a 1 amp, roughly 1 amp load, which is below the overcurrent limit. Things should be okay. Watch the 2 traces on the scope, look at the output voltage meter and the display on the power supply. Here we are at about 5 volts in, drawing 900-ish, an indicated 900 milliamp load. Both scope traces are overlaid at about 5 volts. Bearing in mind that this was 0, 2, 4, 5, 6. Output's indicating a little low. There's a fair amount of drop in these wires. So, as I say, the input and output voltages aren't terribly well, aren't particularly accurately displayed. If I now wind the input voltage up slowly, you'll see input voltage here and on the scope, and you'll see the output voltage. The output voltage is measured on the meter. Watch for the magenta trace on the scope. At the moment, the yellow trace and the magenta trace look exactly the same. Slowly wind the input up. If you look carefully, you can see it climbing a bit on the scope. When we get to 6 volts, watch for the magenta trace. The magenta trace says the output's dropped to 0. And you'll see now you've got a red light, but intermittently you've got a green light. The green light is the self-resetting, momentarily overriding the fault indication, turns the output back on, but still clamped at 6 volts. And that, if I fiddle about with the scope, you'll be able to see in a moment. I've wound the time down to 5 milliseconds of division. And you can see there the output turns back on for about 20 milliseconds, roughly every 2.5 seconds. The input voltage drops, of course, because with the magenta trace at 0 there's no load current. As soon as the output turns on, it draws load current, so the input voltage drops slightly. If I wind the input up, I'm going to wind it up to about 10 volts. The output's still at 0. Uberclamp is still indicating a fault with the intermittent retry. You see the magenta trace. That's the output momentarily turning back on and going to the clamp voltage of 6 volts. You see there's a tiny overshoot there. I'm going to try and tidy up the trace a bit. Let's zoom in. This only triggers on, it only displays you when the output has gone up. So it looks steady, but in fact, if I go back to auto, you'll see it's still pulsing. The output turn on isn't perfect, and there is a very small overshoot. That cursor is on 6 volts, so one of these is 0.2 volts, so there's a little spike up to about 6.2. But the input's up at 10 volts, so Uberclamp is doing its job fairly well. But that shows you what happens if there's a permanent input overvoltage. Let's see if we can wind this back down again. By the way, you can see it doing its protection job to somewhat higher voltages. It does start to have problems regulating the output at higher input voltages above about 10 volts. And in fact at much higher voltages it doesn't turn the output back on again during the retry. But that doesn't particularly matter, or at least it shouldn't if you think about it, because when I drop the voltage the retry continues. If I drop the input voltage back down to 5, or rather below 6, watch the magenta trace. It's turned on. The output's come back again. Go back to over 6 volts. Output's turned off with intermittent retry. Turn the input down. You can't see the meter, but you can see the LED's changing. Meter net, the power supply now says 5.7. So what happens if I've got an input voltage of 10 volts? I've accidentally left my power supply switch to 10 volts. I've got some really expensive hardware connected to my 5 volt output. I don't want to damage that. What happens when I switch Uberclamp on at this voltage? Shall we see? Are we feeling brave? Just need to change the scope settings slightly. Yeah, okay, we should be good to go. That was impressive, wasn't it? Let's try that again. I forgot to set the scope trigger. Here we go. Not sure why my scope isn't showing me an input voltage. Let's try it with normal trigger. Okay, let's go. Now what you see there on the scope trace is the input voltage, yellow trace, climbing up very quickly, 5 milliseconds of division. Uberclamp is clamping at 6 volts for about 20 milliseconds, then it says, no, the overvoltage has been there too long, I'm in danger of overheating, I'll switch the output off. And if I zoom right in, there's no visible overshoot on the output as a result of that input overvoltage. Okay, but that's a fairly slow input transient. That's 5 milliseconds of division, so that's about 5 milliseconds rise time. Let's give it a bit of a harder job. I'm going to put in a particularly nasty, I'm just going to input transient. I'm just going to switch the input straight on through connecting a wire. You'll see it on the scope. There's a certain amount of bouncing because I'm just connecting a wire to a contact. It's not too surprising that the input's a bit noisy, but look at what Uberclamp is doing. That's 5 milliseconds per division. Let's go out a little. we're now, I think, on 1 millisecond a division. And that's me dabbing the wire on. We're now on 200 microseconds a division. That's too much. I've lost the trace off the edge. Oh, that was 100 microseconds. This is 200 microseconds a division. Look at what Uberclamp does in response to that overvoltage. 200 millivolts overshoot for I don't know what time that is. That's 200 microseconds a division. That's less than 50 microseconds overshoot of less than 200 millivolts. This is demonstrating reverse polarity protection on Uberclamp. While I was away, some wag has come along and reconnected the wires to Uberclamp the wrong way round. Last thing I did was demonstrating overvoltage. Power supply is left at 10 volts. Supposing I don't notice and I connect Uberclamp to an input of what is effectively minus 10 volts. These are the input and output voltages the tracer's overlaid. Meter output says 0 volts, tracers say 0 volts. I'm just going to dab this wire on. You see the two little yellow arrows? They're telling you that the yellow tracer's disappeared off the bottom of the screen because it's gone to minus 10 volts. But the output is at 0. Let's do that again. Let's move the input voltage up the screen. And we've got an offset of 6 volts on there. So if I put minus 10 in, it should go down to about there. Watch the output and the input. Well, the output's dropped. That's minus 10 down there. But the input's okay. I'm just going to put the camera down again. Swap the wires back to where they should be. Wind the input voltage back down so it's the right way round. .6 volt offset. Input and output voltages are both 0. Oh whoops, I've just connected my overvoltage back to the output. But Uberclamp is doing that protection thing. If I leave it connected. Now I've got to put the camera down again. There's the protection. Wind the input volts back down below 6. There we are, input follows output. It looks quite complicated. Operation is actually quite complicated, but there's a detailed description at EasyEDA.com, and you can get hold of schematics, bill of materials and Gerbers for the PCB, or order them directly from EasyEDA. Just search for Uberclamp EasyEDA and the web should take you pretty much straight there. I'll try and put a link up somewhere. Hope you've enjoyed watching this and haven't found it too tedious. Bye for now. This is Uberclamp responding to a short circuit on its output. This cursor here is at 6 volts, this is 2 volts a division. The yellow and the magenta trace, yellow is input voltage, magenta is output voltage. You can see here they're down at 0 because all the traces are offset by 2 squares at 2 volts a division down the screen. So this is 0 volts, and you can see that the magenta and the yellow traces are overlaid, so they're both at 0, and indeed output says 0 volts, power supply is switched off. I'm going to turn this on at roughly 5 volts input, so I'll try and get my hand out of the way, there's a lot to see. Here's the green LED has come on, the output voltage has risen. Don't worry about the inaccuracy of the voltage on the meters, they're not particularly accurate. You can see the input and output voltage traces are still overlaid, so they are still at almost exactly the same voltage, but now they are at 5 volts. So Uberclamp is sitting there. The input voltage is below 6 volts, so it's not over voltage protecting. I'm going to throw a series short circuit across the output, and that's on. I've left that there. You can see the red LED flicker. Oops, I'll let go of the short. See the red LED flicker? You don't see the green one come on because of course I've shorted it out, because it's measuring the output, it's indicating the presence of output voltage, and you can see that the input is still at 5 but the output is at 0 with the occasional pip high, because the screwdriver is not a dead short circuit, and the input dips whenever Uberclamp tries to reconnect the output. I've obviously just let go of it there. It's back down again. I'll explain that dip in a moment. It's come on again. I'm trying to hold the camera and hold the screwdriver at the same time and watch the screen, so it's all a bit difficult. If I just leave that and let go of the screwdriver, it's quite happily sitting there with 5 volts in, no volts out, and we've now got a much tighter short circuit because the output voltage isn't trying to climb. The input dips because the moment Uberclamp pulses it on, it's driving 2.5 amps into the short circuit again, so the input voltage dips slightly. You can't really see it terribly well on the input current from the meter here because the meter is heavily damped. And so now if I take the short circuit off, you'll see, I'll try and get the see the red LED here and the green one here. I'll turn the light off so you can see it a bit more clearly. If you watch the traces and the LEDs, I'm going to take the short circuit off. It was a little while before the output came on. That's because if I remove the short circuit, it doesn't turn on until the next retry pulse. So if I try and short it again, there you are, it stays down for a bit, and that gap there is the time from when I remove the short to when the next retry occurs. I'll try and do that once more. Short circuit on, output's dropped. Oh, I've accidentally let go of the short circuit again. And again. There we go, short circuit, output down. No, let's let go again, there it is. Let go of it, and you see it comes back up. I'll do it one more time. Short circuit it, let go, comes back up after the next retry. I'm going to do very briefly short it, or try to anyway, and you'll see as I do that, there you go, now it comes back on. I'm going to stop the trace. You can see that that time there, starting from there, that's 0.5 seconds of division. Let's ignore the quarter second. So that's half, 1 second, 2 second, 2.5 seconds, 2 3/4 seconds is the retry time. The last thing I think to show is Uberclamp is now working okay. Input equals output, start the trace again. I'm going to wind the input back up to 10 volts and you'll see at around 6 it'll clamp. There you go, as I pass 6 it clamps. See the output voltage has dropped. See these little spikes here? This is it reconnecting the output to the load. But it's being regulated at 6 volts, so the overvoltage clamp is working, the retry is working, the overvoltage is about 10 volts. Just to demonstrate that Uberclamp can deal with an overvoltage and an overcurrent at the same time, here we are back juggling the screwdriver and the wires and the scope and the camera all at the same time. Now I've shorted the output. As you can see, the output's dropped, input's at 10 volts, outputs is at 0. It's very hard to see the retry LED, but it is flickering. You can just see it, the camera doesn't show it very well. Let go of the short circuit, output starts pulsing back up to a regulated or clamped 6 volts. Wind the input back down below 6. See there was a retry flash there, still retrying. There it goes at the next retry. We're back at 5.4 volts below 6. That was the input to the output turning back on again. So there you have it. That is Uberclamp. I hope you like it. Got any questions? Just get in touch with me and ask away. I should point out that this was done on EasyEDA, a free web-based schematic capture, simulation and PCB design with optional PCB purchase, although you're not obliged to. You can send your Gerbers to anyone you like. EasyEDA.com. Thoroughly recommend it. Go and have a look, have a try. The PCB was done by them. This is version 1. I made some mistakes on it, so it's a bit of a mess. The PCB that's actually on the website now, you'll find details of how to find it on the in the text. That is now the next version, which has had all these little bits and pieces of extra components removed, or rather mopped up in the circuit design. Enjoy. Thanks for watching. Bye.